This is the second part of our lecture on week 7 of the Advanced Computer Architecture course, CS 470. What we're going to do today is something that in some sense connects to what we have seen in the last 2-3 weeks, that is statically scheduled architecture, but it's actually not completely linked to that. It has been developed as a way to overcome one of the major limitations of these VLIW architectures, that is the intrinsic binary incompatibility of these architectures. It has been used also in other contexts, as we will see today. With this lecture, we will complete the world of general purpose computing. We have seen dynamically scheduled. We have seen in the last 2-3 weeks statically scheduled. And from next week, we will move into a different world of architectures that are developed for very specific applications. The problem we want to tackle today is the problem of binary compatibility. I guess we understand intuitively what it means. We have a binary code, we have an executable, something that has been probably compiled from some higher level language, and it is prepared for a given processor. And then we want to change processor, have a more modern implementation. Maybe it was a simple pipeline processor when I compiled it, and now it is a superscalar. And I want to run the same code unmodified, and of course, profit from the improvements, the microarchitectural improvements of the architecture. Now, the fact that we want this, which is not given, right? Because one could say, well, why don't you take, if you change the processor, why don't you take your C code and you recompile? So the fact that people want binary compatibility has always had a very strong impact on computing. It was certainly something that was not there in the early times of computing. In some sense, designing a computer, designing a new machine consisted largely in designing a new instruction set. But then at some point, when people started refining the microarchitecture, leaving the contract to the programmer, the instruction set architecture constant, this became a very important concern. In fact, I remember once John Hennessy, one of the authors of the textbook that you use, and one of the recipients of the Turing Award a few years back, and the founder of MIPS, among other things, was saying how much, that one of the things that he never anticipated practically at any point in his career was how much binary compatibility will be an important factor in the evolution of the industry and of the field. Binary compatibility is something that people care a lot. Think about what happened, right, in the late 70s, beginning of the 80s, a new architecture that we now call x86 came about. Some processors, pretty crude, pretty elementary, right? But by that time, they were maybe state of the art, but they were very simple from how we can judge them today, started being solved. And then a number of architectures came in that brought fundamental microarchitectural improvement. We have seen, we discussed pipelining out of order, and all these things fitted poorly on the x86. So a lot of other architectures came and competed. Now look at what is there outside, right? That's what is out right now. x86 is there. If I start telling you about alpha or MIPS, you start, I mean, you know MIPS because of the book probably, right? But you've never seen a MIPS operating probably. Alpha came as one of the best architecture and disappeared. And maybe there is ARM that, just because of similar situations to what happened to the x86, but in a completely disconnected context, at least at the time, right? The one of smartphones got a niche of its own, and the niche became a second major computing arena, right? So, but that's what you see, right? All the other incredibly, potentially, I say, better instruction set architectures that came out connected to much better implementations, all gone because of binary compatibility. So in some sense, if you turn the things around, you could say that binary compatibility is one of the most important, maybe the single worst obstacle to the evolution of processors. There are a number of ideas that in architecture you would like to implement, but unless you can hide them under the same architectural framework, the same instruction set architecture, they are doomed. You cannot really introduce them. This is exactly what happened to superscalar pipelining and so on, that looked like difficult or impossible to introduce in the x86 world until someone found a way to do it. This is true still now for things like VLIWs, right? We discussed VLIWs, we discussed also a number of limitations, but they do have some advantage that one would like to exploit potentially. But they have one problem. They are, first of all, completely incompatible with x86, okay. And the second problem is that they are even worse, incompatible between themselves, between generations, right? And I hope you remember what we discussed in the last 2 weeks. So what can we do for that? And what we are discussing today is linked to this problem, right? To how to use, among other things, very long instruction word processors under this constraint that binary compatibility is seen as an essential feature of computers and of processors. So there have been quite a bit of activities in the field of dynamic binary translation, the solution that we will explore today. There have been a lot of attention in academy and in industry, but in a sort of academic research context. To my knowledge, IBM never did anything commercially based on this technology of dynamic binary translation, but there was a commercial processor, a company that has been in stealth mode for some time, and then came to be known, that was selling a processor that was compatible with x86, surprise, surprise, based on this technology. And so we will discuss a bit of some of the aspects. As always, I'm very interested when there are these industrial attempts, right? A bit like Itanium, because somehow they are, I don't know how to say, a bit more credible. It's not good that as an academic myself, I call it non-credible, our research, but our research never goes until the last final detail of making it work. And sometimes maybe that is the killing point. Well, this is industrial, right? This has been shown to work. And one aspect also that I find it interesting of this technology of the dynamic binary translation is that it is an idea that if you had come to me 20 years ago and said, "Oh, I have a great idea for my PhD and I would want to try to do this thing," I would have said, "You must be joking. It's never gonna work." It's one of those cases where you revisit the border between hardware and software, how much of something you want to do in hardware, how much you want to do in software, in a pretty radical way, right? In a sense, is what we have done in the last 2 weeks, right? The same things that we have done before in hardware in terms of scheduling, we decided to do them in software. Here, somehow, you want to do them in software in a different way that we will see. But so it's sort of more extreme, and it seems hard to do this in software in real time, as if you were to do them in hardware. it's a very mobile boundary, right? What makes sense to do in software and what makes sense to do in hardware. I consider myself a sort of an hardware guy, architectural guy, and so on. And yet we love software, right? The software is much better because I can change any time. If I make a mistake, I can correct it. So there are huge advantages in going for software. But you can't do everything in software. Why? Typically for performance reasons, right? It's if I do hardware, if I put my gates down, I do a much better job. And this is a lot of what this course is about, right? If I create an appropriate circuit, I can be incredibly efficient. But then there is always this temptation to go for software, and this is one. And to me, it represents one of those cases of ideas that seem probably revolutionary or crazy at some point in time. Then someone comes and decides that, well, let's try it, maybe proving that it can work. And maybe at some point they become commonplace because things have evolved and the boundary or the possibilities of software move. So I think it's a good example to keep in mind of how our preconceptions of what can be done and cannot be done actually changes in time, which for you starting a career soon in this field and having some 30 years in the future in the domain, well, you'll figure out that it's important to keep open to the fact that what you think will work or not work may become wrong, may be wrong one of these days. So what is the topic? The topic is how to translate, right? How to take the code that is in one format, in one binary format that is the source architecture, call it x86 in most practical purposes because that's the binary files that we have, and having a physical hardware that has nothing to do necessarily with that or not compatible in any case, right? To which extent we may discuss a little bit later in some practical cases, but it potentially completely different, right? Completely unrelated. And this will be our target architecture. And the idea is, okay, so how do I run it? I have to translate, right? I have to do something on this binary file to make it into essentially a new binary file that I can run on the target architecture. So this is the name of the game that we want to pursue today. So how do we do it? Right. I guess the first idea is absolutely immediately clear to everyone, I hope, right? Which is, let's write a program, right? I have my target machine, right? The machine that is here. I can write it in Scala, in C, whatever. I write a program that will run on this target machine. And what does this program do? Well, it emulates the running of the program. What does it mean? It will do exactly the same thing that my processor is supposed to do. Whatever it says in the instruction set architecture and in the processor manual, I will do, but I will encode it in software. I'll say, go and fetch, have a variable that is called PC that represents the instruction pointer, the program counter of my processor. Go and fetch at this address, look at the bits that you get out from this from memory, try to understand what these bits represent in terms of encoding of the instructions in the source architecture, and go execute the correct functionality that is represented in the slides simply by having a function that corresponds to each of the original instructions. I will have registers that are represented by variables in my program, and so on and so forth, right? So this is clearly something that I can always do, right? I'm just doing in software what my hardware is supposed to do. Since it is software, since I'm on a Turing machine, I can do whatever I want, right? Whatever the hardware does, I can do. So there is no functional problem at all in following this path. In fact, you can go and find emulators of old machines, Atari or whatsoever, of the 80s, 90s, and run them on your PC, and to a large extent run any software on them. The problem is performance, right? The problem is that, well, you can imagine, right? The moment I'm writing a program, maybe even written in C on Scala, that goes and fetches a couple of instructions in my in my target machine. Then I have to analyze bits, which is always something a bit painful in an instruction set. I need to spend a few instructions for the analysis of the different bits. Then I have to do a branch probably to do a different functionality. You see where I'm going, right? It cannot be very efficient. I have in mind something like at the very best, 10 times slower than running native code. I think it is, I don't know where I remember this number from, so I don't know even if it is correct, but I guess that if it is correct, is really, really the best case that you can do, right? Again, think how many instructions you have to write in the target architecture to emulate the functionality of a single instruction in hardware on the source architecture. So great, I can do it, but then when I buy a new processor and I run on the new processor this, I'm happy because my new processor is 50% faster, but then I take a hit of 100 of 10 of a factor x 10x in the performance, and I lost all my advantage. So I buy a new computer and I go much slower than before. So it's a terrible idea, right, in terms of performance. So then what else can I do? Well, I can try to be a little bit smarter and really say, okay, I want to really translate, right? I have a piece of code, I have a piece of binary that works, and let's make once and for all an equivalent piece of binary, but that is now targeting my target architecture. You can think it in a fairly simplistic way, as the slide suggests, where you basically make some sort of analogy or correspondence between the registers of the source architecture and the registers of the target architecture. If you are lucky, or if you do things properly, if you are creating the target architecture, you'll make sure that you have, for instance, enough registers in the target architecture to have always a correspondence between the source register and the target register, right? There are enough target registers to have the representative of all the original registers, so that you don't have any issues in terms of representing the registers and the storage. And then you can try to have similar. In most architectures, you have essentially the same classes of instructions. So in most cases, you may have a one-to-one correspondence. So this is a simplistic view, not necessarily a wrong one, right? But it may be tough to do this. It's actually something that is as old as computing. As I was saying before, there used to be a time where making a new computer was essentially making a new instruction set architecture that could be implemented in a powerful way. So people were used to the fact that the instruction set changes, and static translation to an extent was used for that purpose, right? And it was usually a process that was a bit trivial, if you want, as this slide suggests. Or you have jump and link label in MIPS. Well, you have to do call label, that is essentially the same thing. You start imagining already, no, it's not quite the same thing, but still it's more or less the same thing in x86, and is a sort of one-to-one-ish correspondence. You can also do this in a much more clever way, right? Especially today, maybe you will not have done or thought of this in the 70s, 80s, and the better idea of thinking of this is to say, well, look, the binary, the assembly code maybe of the corresponding to the binary that you have for the source machine is actually a language, right? Has these instructions have a semantic value. You know what they do, right? So what you can do is to treat it as a language, right? And so you do a front end is like a C compiler. Instead of being a C compiler, it takes this strange assembly language as an input, converts it into an intermediate representation, right? Now it's like the intermediate representation that I will get from C, right? It's an intermediate representation, and now this intermediate representation, I connect a backend for my target architecture, and I spit it. It's essentially the same thing, right? It's not very fundamentally different, but a number of problems don't exist anymore. I'll do instruction selection properly, so I find out the right instructions that I need to implement any functionality. I will not have problems in the number of registers available because I will do a new register allocation, and if I need to spill something that I was not spilling on the source machine, I will do that, and it's not a problem, right? Okay, so all this is good. Whether I do the simplistic, trivial idea or I do the good idea, it seems that it's a good idea, right? It should work. And it also seems maybe that the performance problem doesn't exist anymore, right? Think about it, right? It's I'm basically substituting the instructions or the encoding in one architecture with the encoding in the other architecture, but I'm really recompiling in some sense. So why am I going to be worse, right? If my target architecture has a good compiler, or even simply has a good backend of a compiler, I'm done, right? I'm as good as my target architecture can be. So this is one of the cases where you have to stand one of my suggestions of doing a pause. I will ask you to pause for a second and think what can go wrong with this static translation. Why is not such a great idea as it seems? There are actually a number of reasons, not only one. All of them compound into making this essentially impracticable for today's machines. So let's do a little pause, and I invite you to really pause and think by yourself, what can go wrong? I hope you followed my suggestion, my humorous suggestion to always answer if there is a problem, what is the problem, must be exceptions. It's true. Also here, exceptions are one of the problems. They are only one of the problems, maybe one of the most severe, but still one of the problems. There are many others that make this idea of static translation not really practicable. So if I'm starting not from the assembly code, right, from the assembly language, the .s maybe in many architectures, but I'm starting from the binary. One of the problem that I have is a completely seemingly trivial one, which is to understand which bytes of my binary correspond to code. And it's not sufficient to say whatever is in the code segment, if you have any idea of how an executable is usually packed and organized. It's not sufficient to be in the code section to be code, right? I can have in the middle of code, is not illegal and is not impossible that I have strings, right? Or pieces or tables or little pieces of data that are not instructions. And so how do I find out what are instructions that need to be translated and what are not instructions, which on the other hand should not be translated because they are data? And what are these data? Because sometimes the data need to have some adjustment. think about it. It's a very hard problem, right? It seems trivial because you say, okay, what can I do, right? Let's be engineers, right? We try to think of the problem and solve it, right? I start. Sorry, I start reading the code, right? And while I read and translate the code, I figure out where I jump, right? Where is the next destination? Where if I have a jump to here, I know that this is an instruction, and from here I can start reading again. Unfortunately, programs are not always guaranteed to be so simple, right? Sometimes I have jumps that depend on the data. One typical case is that I have a table and for a switch, right? And I compute an index in the table, and I go in this table and I find an address, and I use this address as the destination of a jump. Now you see already that this becomes more complicated, right? Because you have to understand that this mechanism and this computation is taking place to know what is happening. If you understand this, you also understand that the table, the address of the destination in the table, this table that is data, so should not be translated, is actually made of pointers to code, right? And so if you are creating a new version of the code, the pointers will not be almost certainly correct, so they should be changed. So now you have data sets, embedded data sets that should not be changed, code that needs to be changed, embedded data sets that need to be changed by understanding what is happening. One simple way to say all this is that essentially you need to exponentially enumerate all possible paths of execution to really know what is code or not. And this is in general not possible. And even if you use some heuristic, it may be terribly difficult to have something that works. Another problem that there is, and is another problem that should not exist, in fact, is the fact that people do write self-modifying code. And you understand what that means, right? I just write somewhere in the code section, in the part of memory that represents code, some binary word, and this binary word represents an instruction, and then at some point I arrive there and I execute this instruction. So this instruction was not there in my binary, but is there during execution. It used to be, I'm not sure it is used very much anymore, but maybe it is, in fact. It depends very much on the type of code and who writes the code, but it used to be used for protection mechanism, right? You don't want to show some instruction that is critical to your protection. People will go and disassemble the code to try to find this instruction, figure out where it is, and modify it in your binary code so that they annihilate, eliminate your protection, but you will not put that instruction in the code so that nobody can find it. You'll just put it, write it in memory a few cycles before the PC gets there, then jump there, execute that instruction, and maybe rewrite it with something else just afterwards. So that unless someone has a way to look at your memory exactly before or after, within tens or hundreds of cycles, before or after the use of this instruction, and therefore the moment you are effecting some protection or something that you don't want people to discover, unless people can see this within these very short time windows, as I said, there is no way they can debug, right? So this used to be, and I really don't know how much people do these things today, but used to be something extremely common, right? Any piece of commercial software will do something like this, and maybe they still do today because we still have protections, licenses, and so on, and they are probably written in similar ways, perhaps. And then there are exceptions, right? Again, this is my favorite, right? There are exceptions that create problems. Imagine some silly examples. For instance, I have a load instruction that if there is a TLB miss, has two slightly different behaviors in the source and in the target machine. In the source machine, the exception PC, wherever it is, and of course this is part of the translation, but the exception PC as the address of the load that didn't get to be executed because of the TLB miss, and maybe in the target machine, it points the next instruction instead of the same instruction, the instruction after the load, right? So it may be very difficult to implement because you're only translating, right? You're not rewriting the exception handler. If you are translating the exception handler because you have the complete operating system, right? You may want, it's legitimate that you want to translate the complete code of the source machine. If you are translating the exception handler, well, if you cannot not understand what is going on because you will need to get the translation to work, to change accordingly the value of the APC. I mean, when you read the exception PC, you may want to decrement or increment whatever is the direction to simulate the behavior of the other architecture, right? But this implies some sort of understanding of what the code is doing that is not part of the game of the translation. So it makes everything significantly more complicated. The basic result is that static translation doesn't work. Nobody ever thought seriously to do a serious translator and say, let's take a code from x86 and let's have this beautiful processor that is called Alpha, and let's translate everything and use the Alpha processor instead with the Microsoft Windows working and so on and so forth. I'm not sure that actually nobody thought of it, but nobody thought seriously or managed to get any close, to my knowledge, to do this. So what can we do, right? We have these two words, the emulation. There is no problem in some sense, right? I can do everything. It's just software. So I will do whatever I need and whatever I read in the manual, in the specification of the processor. But it's terrible because I'm one level of abstraction away. I'm doing software instead of hardware. Or I do translation that works super well in terms of performance. If I do a good job, there is no reason that I'm not going exactly as well as on the source architecture, but I cannot really do it. So what is the idea? The idea is a bit, let's make both, all right? Let's combine both, right? And the idea is basically all contained in this in the flow chart that we are going to see in this slide. Essentially, we do emulation. We interpret the instructions. We read, fetch, and execute the instructions as in an emulator, right? The only thing that we do is that we try to group instructions in and create some chunks of code that somehow stay together. What are these chunk of code? What are these groups? Is not particularly important for us. One way that you can look at it is to say is a basic block. Anything that is between two jumps or branches is a group, right? In fact, I think that people want typically to have something a bit bigger than that. So the algorithm, the definition of what is a group is maybe more complex to create larger groups, but it doesn't matter to us. So in your head, you can say, okay, a group is a basic block, right? And so you take the instructions and you continue to emulate them until you arrive at something that signals the end of the group. So again, in our simplistic view that a group is a basic block, if I find a branch or a jump, I am at a stopping point. So if I don't find that, I continue to interpret, I continue to do the job. Is a poor job performance-wise, but I can do it, there is no problem. If I find a jump, what do? I close the group, I register the fact that I am in a new group, and I ask myself a question of this new group, whether I've already seen this new group, right? I've done the jump, now I am at another PC at the destination, and I say, have I already been here? And I wonder if if this destination, for this destination, I already have a translation. Now, of course, the answer is no, because I've never spoke and I never said anything of translation, right? So let's forget the yes branch and let's look at the no branch, right? Then I ask myself, if I already been here and there is no translation, have I seen the group at least a number of times, right? Say 30 in this graph. And if the answer is no, then let's forget about anything. I'm in a new group, and I continue to do my my interpretation and go on. And so here is, I'm in this loop until the next group. I find another group. I don't have a translation. I've seen it many times, maybe not, and I continue, right? So essentially, to a large extent, initially my machine runs in the upper half of this and is an emulation loop, right? It's just doing emulation, gathering some information about groups of instructions that sort of stay together and so on. And the whole idea is that as soon as I've seen a group a sufficient number of times, and therefore I understand that this area of code is an important part of the code that is important performance-wise because I'm executing it many times, what I do is that I take a big detour, and is a big detour, and is this what I would think make all this idea fail miserably, is I go into essentially a compiler, in the sense that I take the group, I take what I should be starting to emulate, right? If I have, if it was a no, I will start emulating this. Instead of emulating, I take it as a piece of code and I compile it. I compile it for my target architecture. Why am I saying compiling and not just statically translate? Because maybe my destination and my target architecture is actually very different. For instance, it's a VLIW and I have x86 code. So I have to schedule, I have to find parallelism, extract instruction level parallelism. So I think it's more correct to call it a compilation task, a bit like I was describing before. I'm interpreting the instructions as a language. I do an intermediate representation, and I do whatever my VLIW compiler has to do to create a translation. Now that I have a translation, its program is essentially what static translation would have done, right? Now that I have it, I can execute. Its native code is very efficient, and I'm going very fast, and I obtain the same value, the same result that I would have obtained by going on the path on the top of the slide, but I have done the green path, and I have more efficiently executed. And now I find myself again in the next group, and I ask myself, is a translation exist? And so on and so forth. And after some time, for most of the pieces of code that matter, I will have a translation, so I will stay here. So you see how my execution moves during time of execution of my single execution of a program, starts in this loop, as I was saying, right? The top loop, actually this inner loop many times to end the group, and then restart a new group, emulate, restart a new group, emulate, and so on. We start like this, and automatically we tend to go, and by the sort of end of the execution, be largely in this loop. And this loop has the characteristic of being performance-wise perfect, right? Because when I'm here, I'm not translating anymore. I don't have any hit on performance because of the translation or recompilation, if you want. I'm just executing native code with some glue logic that checks if I know the translation, where is the translation, and then I go for the translation, right? But I'm essentially as efficient as if I had managed to do a static translation. Okay? Seems a great idea. I hope we all understand that the part that is critical here is I stop, imagine, right? I am in Word, uh, Office, right? Microsoft Word, and I start to do something, anything, right? Typing a character and so on, and it's the first character that I type, suddenly my Word stop running, and my Word or my computer starts compiling the next piece of code that Windows need, right? And if you have ever used, I don't know, GCC or something like this, of course, this is not GCC, but still you understand the amount of work that you're doing is not non-significant, right? It's not a few instructions more that I will never notice. But in fact, it is, right? So people manage to make it in such a way. I never tried to use one of the Transmeta processors, but it was sufficiently smooth for this never to have been evoked as a problem. So what I do in this translation, what I do in this compiler, well, essentially I do maybe a lightweight version of most of the things that that I will do in any compiler, and especially in any VLIW compiler, right? I will do all the scheduling, I'll do all the data and control speculations that we have discussed, I'll do unrolling if I need, and so on and so forth, right? All the things that we have seen in the last 2 weeks, again, maybe in a lightweight manner because I need to do them very fast, I can do them here. One of the questions that one can ask is this going to be slightly better situation to do this kind of compilation for VLIWs here than, let's say, last week when I was doing it from high-level code and from your piece of C code, and I was going to try to produce VLIW code? Is it any easier to do it here? And if you think about it, what were the components or the information that was making it particularly difficult for us to do the compilation? Many of the times was to, for instance, understand how often a branch is taken and is not taken, right? It would have influenced things like knowing whether you predicate a small if then else or not, depending on the predictability of the branch, right? And we said something like this, or you need to have prediction of branches to do trace scheduling effectively, or any of the similar techniques of optimization of basic blocks. You will need some information also to do loop unrolling and so on and so forth. Now think, what has changed here? Why it will be maybe a little easier here? Well, let's go back to this, right? The moment you start to translate and schedule, or I say to compile for the VLIW, you're actually running the program, right? You have actually seen a number of times the piece of code that you're going to translate. So this is extremely powerful, right? Because while you are emulate, you're doing software, so you can do whatever you want. You can actually collect a number of statistics. Of course, you cannot abuse of that because it's performance, right? You are slowing down your already slow emulation to collect statistics, but you can collect statistics and way above potentially informations like the branch results, the branch directions, and so on. You can take more information, whatever information you want, the dependencies between load stores and so on, and you can potentially use them to make better decisions in the compilation. So all those things that looked horrible until last week because we said, oh, we don't have this information, we should ask it to the programmer, we should ask the programmer to run a sample program so that we infer and get profiling information that we can use, and so on and so forth, now actually come for free, right? I'm executing and I observe whatever you want to observe, I will observe, and I will use it to do a better job for compilation. So it's actually sort of very interesting from this perspective. So we're doing something which I want to show this slide to have you appreciate how dramatically new it is in some sense, right? We are used to have a processor, and the lowest layer is the operating system. Maybe these days there is also an hypervisor or something, but in some sense they are just layers that belong, lower layers that belong to the operating systems, to a stack, like in the operating system there is a kernel, there is now also an hypervisor, and then there are all the libraries. There is a continuum of less and less low-level information until you get to the applications, and maybe the lowest application is a compiler, right? And now what happens? What happens is that you have this processor, maybe because I'm thinking of Transmeta in particular, but it doesn't have to be necessarily a VLIW processor, the operating system and the application, but below the operating system, there is a DBT engine, a dynamic binary translation engine, essentially the program that implements this finite state machine, this flowchart. This is radical, right? And it was very radical in the Transmeta incarnation of the idea, because you buy a processor from Intel that is this box, right? It has pins, right? And there is no software in it. Well, you don't think there is software in it. And it's just the instrument to execute your software, but it is not software per se. And now you go to Transmeta and you buy this box, including the pink part, and this is the processor with the pins, right? The piece of hardware that you buy. But the piece of hardware that you buy has inside a compiler, right? And this compiler lives unseen below the operating system of the host, of the processor you have. And this was exactly the arrangement that Transmeta had, right? There have been some, I think, laptops from Sony that use this processor, used operating system, of course, Windows. The compatibility with was with x86, so the application were Office and Word and whatever you want. And inside the processor, you would have this engine. So what does it take to do? So this is how the processor, one of the, I think they did a couple of versions, Transmeta did. One of the first they did looked like. It was a VLIW, and it wanted to be a VLIW that was actually much more true VLIW than the Itanium that we have seen, much more elementary or basic VLIW, close to really the simplicity that one expects from a VLIW. And here you see it, right? It's a 128-bit very long instruction word with 64 general purpose registers and 32 floating point registers, the FPU and so on. So nothing surprising, and the kind of thing that you want. with a few add-ons that don't belong necessarily to the to the basic VLIW. Two of these things are easy to imagine what they are. There is here some local data RAM and some local instruction RAM, right? So it's essentially like all these machines, like all our modern machines, they are intrinsically machine with a separated instruction and data buses. So on each of these buses, you have some memory. Why do you have some memory? Because now you have this hidden program, right? This is not, you cannot malloc to say, give me a piece of memory in the main processor memory so that I can put my compiler, because the compiler, my compiler doesn't exist, right? Again, this is the figure that you should think of, right? This is below. The application asks the operating system, please malloc me some memory, but the DBT engine is below, right? So the operating system is actually using the DBT engine without knowing it, and the DBT engine cannot communicate up. So maybe in some ways they did it, but in the simplest incarnation, or for the lowest level part of this, I need to have some RAM that nobody knows that exists. I have actually, I find surprisingly small amount of data and instruction memory. We'll come back to the other pink parts in a minute. Similar thing is the kind of system that IBM was proposing in their open source simulator, emulator of this kind of idea. Again, IBM, to my knowledge, never implemented this for real, but had a complete system, open source, that people could play around with and make research. And you see the variations are essentially the same. The PowerPC becomes this VLIW, and then there is part of the memory and part of the ROM that are reserved to this DAISY, which is the dynamic binary translator. Okay, so it's time to come back to the usual question, where are the problems? What is going to create the problems? Or actually, maybe here the question is going to be slightly different, is how come, if in the end we are doing a translation, because in this corner, if I go back, in this corner here, what I'm doing is exactly what I was describing as a static translation, maybe a refined one, but still a static translation. How come that these problems don't exist anymore, right? We had problems before, we stopped to discuss them, and now suddenly, why they are not here? Maybe it's worth a pause so that you can go back a little bit into that list and see which one have disappeared naturally because of the way we are doing things here, and which ones are actually potentially still there. So let's do a pause. If we try to remember the list of problems that we discussed before for static translation, the first one I think was the code discovery, right? How do I find out code? Now, this is a problem that is naturally gone here, right? There is nothing that I need to do to get rid of this problem, because I am in the middle of the emulator, right? The moment I decide to translate a piece of code is because I've been emulating this piece of code 29 times before, right? Again, 29 and 30, I don't know, is a number that probably I took from DAISY, but a number of times I've been emulating. So there is no problem in discovering code, right? It is there. So that problem is gone. Self-modifying code is a bit the same advantage, maybe. I'm terribly tempted to do a pause again to see how you will solve the self-modifying code. Try to think a bit for a second, right? The problem is that I have someone that is going to write, I mean, the program that I just maybe translated is going to write a specific instruction, the binary of a specific instruction somewhere in some position in memory, right? So this is not gonna work, right? Because now I am in the middle of my VLIW code, and someone is going to take some strange sequence of bits that mean absolutely nothing for my VLIW processor, and is going to write this thing in the middle of my code. So there is also the problem that maybe is no longer at the right place in the code, because of course it has been translated and all the code is in a different place. But anyway, somewhere in the middle of my code is going to write this garbage of bits that corresponds to x86 instructions that mean absolutely nothing to me. And either I'm avoiding them because they're written in the wrong place, but then I'm not going to do what the programmer wanted, or maybe even worse, I don't know which one is worse, I'm going to fetch them and execute them as if they were VLIW instructions, and of course, they are garbage, and I'll do I don't know what horror, right? So either way, that's not gonna work. I don't resist, I have to make a pause. Is there something that I can do to realize that there is this problem, that someone is trying to do this? Actually, before doing the pause, let's think of, if I can identify that someone is writing some x86 instructions in the middle of the code, which is a question that I will do a pause for, but if I can do this, do I have a solution? This is perhaps easier, right? Because if I go back to thinking at what is my my system now, the moment I see, right, the moment I'm here and I want to execute and so on and so forth, and I see that something has gone wrong and someone has written in the middle of the code, I can always forget about the translation and go back here and emulate, right? So I can always accept this is a major difference, right? It's a critical difference with the static translation. The static translation, I have somewhere a translator that is a program someone uses once in life and gives me a piece of translated code. Now I can only use the translated code. If someone tries to modify, there is nothing I can do, right? I cannot figure out what the original, source new instruction that has been written in memory really represents. I'm screwed. Here, the translator is here, but better still, there is an interpret. There is an emulator. So the only problem that I really have is to detect that someone has changed something. If I detect that someone has changed, I can forget about the translation and go here, basically invalidate the translation, forget that I have it at all, and go to interpret. And now if someone has written in this original code something, well, I will execute it, right? So I'll go back to my question and my pause. Is a good exercise to think for a second. What do I do? How do I have a way to find out that someone has written somewhere in my code, or actually somewhere in the original code, better still? Pause. Okay, I hope you see this, right? It's one of the sort of, there are a number of things that depend on this mechanism that we need here. So let me repeat what is the problem, right? The problem is that I have my VLIW, so my translation, my translated code, that is trying to write at a specific location in memory, or at a location in memory that is in a specific area which corresponds to my original source code, right? I have both of them somehow in memory, right? I have in memory the original binary, and I have this translation. And the translation, since I didn't do any magic to try to understand that there are pointers to the code and so on, because are the kind of things that we said before, are extremely difficult for the static translation to really understand, I didn't do it, right? So it's writing in the source code at a specific location a word. And this is a standard write, right? A standard store in my VLIW or in my target architecture. So how can I figure out that someone is writing in a specific area of memory? Well, the question is, the answer comes from the fact, from asking the question, what is in between my load store unit in the processor and the memory and the first level cache? And there is only one thing, and is always the same, but extremely useful piece of hardware, which is the TLB, right? I need, in all these systems, to translate the virtual address I want to write into a physical address so that I can actually write in memory this modified instruction. So what is the solution? Well, the solution is to hijack somehow the TLB to do the job that is not supposed to do, but I want it to do, which is to tell me when someone wants to write in the code. So what I can do is to mark, for instance, it will depend on how my TLB is done, but for instance, TLBs typically have the information where some area is read-only or not, and code is not necessarily read-only, right? Otherwise my self-modifying code will not work, but I will mark it read-only. And the moment it goes in the TLB and I try to write there, since it is read-only, it will raise an exception. And since I get this exception, I can look at what is happening and figure out that someone is writing in the code. So this is self-modifying code. And this is exactly what I said before. I need to know. The moment I need to know, I realize this, I can simply switch to the emulation mode, and everything will work fine. So here is my detector, right? The question was, how do I detect that someone writes code, replaces code, modifies the code with new instructions? Well, they are actually, it's actually through the TLB. Okay, so some of the problems disappear, maybe with a little bit of work, but disappear. So what happens, for instance, of exceptions, of precise exceptions? So see, exceptions are always around as one of the problems, right? It's the usual story, right? There are asynchronous exception. If it is an IO instruction, IO exception, right? Like an interrupt, like some of the peripherals that want the attention. It's really not a big issue, right? Essentially, what I can do is to delay it until the end of the group and then do an emulation, not even necessarily in translation like the slide says, right? I can simply even go to do emulation for the exception handler and jump there, invoke it as soon as it is comfortable for me. The problem, and actually the real problem that we had when we say here precise exception, that was a problem in including static translation, is the fact that the semantic of all the exception could be different, especially in the case of synchronous exceptions, like a TLB miss, not the TLB miss that I just introduced myself for the self-modifying code, but because of a real typical page fault that may happen in the architecture. And here there are all the difficulties that I was evoking in understanding how exactly function the exceptions in the original architecture with respect to the target architecture and how the translation can be done. And we said it's difficult, it's virtually impossible to make a proper translation. So what can I do here? How things are different here? Again, the key of the story is that I have an emulator there available. So I can use the emulator when I have this kind of difficulties, because the emulator will do whatever the source architecture should do. Will be inefficient, but who cares inefficiency, right? I have very few, the exceptions are not the dominant part of my code, so my exceptions will be essentially inefficiently handled, but who cares if it is a factor 10, even a factor 100, it's probably irrelevant, right? So the idea is that as soon as I have, I am in translated code and I see a synchronous exception during translated code, what I want to do is that I want to go back and say, no, forget. We cannot use the translation because something bad is going to happen. Remember, it is a synchronous exception. It means that it happens every time that I execute that piece of code. So I execute again that piece of code, but actually not the same piece of code. I'm going to execute the source, the emulate in the source architecture that piece of code. Now, if it is the semantic of a TLB miss and so on is the same, right? It's sort of if it is a synchronous exception and it happened from the VLIW side, from the target side, it will happen also on the source side, except that I'm emulating, and except the fact that then when I'm emulating, there is no problem whatsoever. I invoke the exception handler, I emulate, or I use the translated. No, it doesn't matter too much, but I could also invoke the emulated exception handler, and everything is fine. Okay, so is it clear the mechanism? The basic idea is that I discover the exception, I forget that it happened, I go back to some previous state before this happened, and I continue. But I continue in emulation, so again, something bad will happen, but now I can cope. So this is terribly elegant, right? There is one problem though. What does it mean, revert status? And this is exactly why we had these additional registers that we have been seeing before, and why we had this store buffer. So I go back to the figure because maybe it's more immediate to see it here, right? The point is that every time that I go from one group to the next one of the things that I do that is not on the flowchart before, but I will do it, is that I make a snapshot of the situation, a checkpoint. I'll copy all the 64 GPRs into the shadow GPRs, and I'll copy the 32 floating point registers in the shadow FPRs. I'll try to do this in a most efficient way, probably by designing these shadow registers and shadow registers appropriately in VLSI when I build the processors. And I close the store buffer and I say, you keep the stores and you don't store actually anything until I tell you. And then I start executing a translation. If now something bad happens, that is, if I get an exception, a synchronous exception, what do? I revert the status by taking everything that is in the shadow registers and I put it back in the normal registers, and by throwing away whatever is in the store buffer and emptying it. And now I start emulation, but now I am exactly at the same situation that I was at the beginning of the group, so I can go and emulate the group. Now, if you remember, I said, actually, with the videos, you can go back maybe and listen to it. I said one of the nice things of going and reading a paper by Pletskun and Smith about the the implementation of precise exception is that they review a number of ideas about how they could do a superscalar out of order processor that implements precise exceptions, and they enumerate a number of them, a number of possibilities, and they decide for one, which is exactly what, with minor differences, but is essentially what we do, this reorder buffer and so on and so forth. But I told you, look at it, right? There are other ideas that did not make sense in that context, but may make sense in other contexts. And one of them was having a shadow register and copying everything from the shadow register. Wow, beauty, right? It's here. It's maybe 30 years later from the paper, now 20 years later from the paper, maybe. But here is a different context, completely different context, but it's exactly the same problem. And the context is such that I really want to go back because I want to redo everything in a completely different way in this case, which is the emulation from the checkpoint on. So it is actually perfect for the other technique. And there you go. Here you have the other technique that is used. Of course, if I don't have exceptions and I arrive to the end of the group, whatever in the shadow registers is just going to be overwritten with a new checkpoint. And what I do of the gated store buffer is that I open it, I start storing all the things that need to be stored, and then I close it again for the next group, right? Extremely elegant and works well. It does everything, right? So does this approach work? Again, the beauty is that we have seen some actual real processors implemented this way, not many, because unfortunately Transmeta went down pretty quickly, as often is the case in life and in the tough life of startups, right? This was a very big startup, but still a startup that was trying to come up with a product, very competitive product that was extremely hard to put together. But as often it happens, the reason for going down was not technical, was not that they didn't manage to get it to work, which maybe would have been my first guess, right? Or it's so difficult that maybe they'll figure out that there is something that they cannot do or cannot do efficient enough. But they went down because of logistic problems, in fact. If I remember well, there was TSMC that was fabricating their chip. They were doing the chip in the most advanced technology node at the time because they needed to fight against Intel, and so they could not afford to be one technology back from Intel, so they needed really the latest technology, except that TSMC had manufacturing problems in the new technology, and this delayed significantly their shipments, and enough that I think Sony at some point, who was the only buyer at the time of the processor, said, "I'm sorry guys, but I go to Intel." At least this is the story that I know and I remember. Anyway, the point is Transmeta had one of these processors, and although it was not incredibly competitive in terms of performance, actually it was not. I think the Pentium 3 500 megahertz was not the latest Intel processor at the time, but was competitive enough, and they claimed they had different advantages like power. Here you have some information about the DAISY, how much ILP they managed on different spec. I think these were the spec of the time benchmarks, how much they would manage to issue so the level of instruction level parallelism in terms of instructions per cycle, IPC. I suppose that the vertical axis is IPC, not ILP. And you see that it is a pretty reasonable amount of IPC. And here you see an assessment for DAISY of the elements that contribute to the CPI. So the previous one was IPC, so instructions per cycle. So the highest, the better. The best. Here it is the CPI, so the cycles per instruction. So the higher it is, the worst. And here you see basically the breakout, because it is a simulator, so you could do these things that maybe would be difficult to do on a real chip. The contribution of so what slows down, what elements slow down. So the red is the sort of baseline. If I had infinite resources, this is the time that this is the lowest CPI that I can get, and then a number of things come on top and worsen up my my performance. Don't ask me why the finite resources are shown negative in compress and go. I don't understand, and I'm not sure you can find an explanation in the original paper. But there is something else that I think is extremely surprising in this graph. So you see again, these are realistic benchmarks, right? These are come from spec. They are things like GCC or TPC. Actually, this is not spec, right? It's a database. Benchmarks, compress, Perl, so things that we know and we understand. And if we were in person, I will stop for today. I'm in generous mood, and I'll not stop again for you to think and try to guess. But you can sort of, to me, there is one thing that I see here, and I say, "Oh my God, really?" And what is this thing is the fact that translation is almost never, nowhere to be seen, right? So this is the bad part of us, right? We'll see another graph later about which amount is emulation and which amount is execution of translated code, which is also an important fact that somehow is not in this graph. But look at here, translation, right? Translation is invisible almost anywhere. Maybe there is a little bit here, and the only place where I see it is our usual culprit, right? Remember, we said already GCC was the usual culprit also when we were looking at the branch prediction difficulties, and GCC, because it is a very large code base, very control dominated, is very difficult to predict. The branches is the one that is more difficult to predict. And here is, in a sense, I think the same phenomenon, right? We go in many different places, many different times, so it turns out that the translation, the code that needs to be translated to run GCC is a larger part, or is more frequent than in other programs. But still, the point is, it's irrelevant. And this is really what I would not have guessed if the hypothetical PhD student would have come to me 20 years ago and said, why don't we try to do that? I would have said, there will be at least as much as the red bar that adds upon the basic CPI. It's not the case, right? So it's a great idea. That's what I want to say. So if I suggest that you read some of the papers, especially the IBMs. Not actually, I'm not sure. Maybe also the other papers from Transmeta are nice to read. Again, they are not particularly important for the exam. And again, most of you heard don't ever read them, but I think it's beyond the economy of the exam. I think they are interesting to get a sense of the ideas that are behind this. One of the things that the papers, I think it's in particularly papers by IBM, they discuss is that there are a number of optimizations that are beyond what you will do in a normal compiler, beyond what you can do in a normal compiler, right? One of the things that you can try to do is to, for instance, relay out the code in such a way that you have more cache hits as possible, or more or least page faults as possible, by having commonly used pieces of code that are used more or less at the same time, that belong to the same page, so that when you bring in one from virtual memory, from disk, you bring also the other parts that you're likely to use at the same time. Typical compilers don't even try, I believe, to do these kind of things, because they need a lot, for at least for the non-trivial parts of that, they need a lot of runtime information. Many of these things may not be even feasible in normal compile flow, because, I don't know, maybe my code mixes up very closely with some library code, right? And these, of course, they are resident in completely different parts of my executable, because they have been linked at a late stage, right? They come from completely different sources. So nobody could have put them very close together, right? But now I'm executing, I'm translating, and I'm constructing the binary code for the target architecture now on the fly, right? And so I see these things, and I can just exploit them. They cost me nothing, right? They are there. I observe them. Why don't I try to do better? So this is a bit the idea, and again, you have some advantages, some side advantages that are not the reason to do it, but why not? You can, for instance, use the translator to hide hardware bugs, right? You can give software patches by changing the optimizer. You can avoid using some instructions that are defective in hardware, right? Although there are sneaky ways that Intel does a little bit of that, right, through some microcode that probably they have. And I don't even know how exactly it works, but I suppose that they have some microcode generators in the decoders, in the complex decoders of their architecture, and so they can actually rewrite some firmware for their processors. I think they have been using this for some of the attacks like Spectre and so on, to essentially disable some of these features that were problematic. But so, although Intel can do some of these extremely small of these things in very particular situations, here you have a translator, right? So you can do almost everything, right? You can have really complete, even functional units that don't work, and you can figure out how to go around them, right? And so it's extremely powerful for vendors to try to have, for instance, silicon out with less testing, right? Which is one of the terrible things that happen today with us, with almost any electronic device, is that you get it until you get an update, you have plenty of bugs. So it's not a great situation to be in, but it's something that vendors may like, right? There have been a number of advantages. One of the advantages that the Transmeta was putting forward, I never understood exactly the argument, but tend to be the low power consumption, right? Somehow there is this sense that being a VLIW, it will be more efficient because it doesn't spend time in the scheduling. Of course, it spends time in doing millions more instructions for doing the scheduling in software, but maybe it does it sufficiently rarely that it compensates. One thing that I find interesting reading the Transmeta paper is that the first thing that one will think is that, okay, so then the source architecture and the target architecture are two completely independent architectures, conceptually, it's certainly true, right? That there is no reason, fundamental qualitative reason why they should be similar. But in a quantitative sense, in terms of ability to do efficiently the job and having this compiler extremely minimalistic in the job that needs to be done to create an effective schedule on the VLIW, the machine, the VLIW of Crusoe, for which I think on Moodle you have also a couple of pointers, if they are still valid, to pages with some people that reverse engineered and tried to figure out how the VLIW works. This VLIW that is inside the Crusoe is very, very strongly characterized or optimized or designed with in mind the fact that IA32 x86 code will be run on it. So condition code registers are there exactly like in the x86. The internal floating point formats are the same, and a number of things that could be different are actually done the same way to simplify the translation and let's say recompilation. Now, one of the things that I find extremely interesting of this idea that did not go anywhere in practice, but spawned a number of research maybe 10, 15 years ago, and I think it was a very interesting, again, experiment, thought experiment to pursue for a little time, is why don't we do the same technique, but we do it not for a different target architecture, but for the same source architecture. So why would I do that? Well, we said it before, right? The advantage that I can have when I am compiling inside the DBT engine is that I have a lot of profiling information of wildly different nature. I can profile whatever I want. I'm in an emulator. I mean, how difficult it is to remember the last 10 values of a variable if I want. Of course, it is a performance issue, but in terms of implementation, I can do whatever I want. So why don't I use this information to compile better? And so one of the ideas that that also come in the picture is, why don't I create something that is similar to the DAISY virtual machine or to this DBT engine that is inside, I think it was called CodeMorpher, because it was a beautiful commercial name for the Transmeta DBT engine that sits above the processor, and I actually displace it. I put it above the operating system, because the operating system, I do it for my machine. I don't care to optimize it further because it's great. Now I get a lot less problems, right? Because now I have something that is just I mean, all the exception issues and so on go away, because they will be treated between the HPUX is the operating system and the processor, so I don't touch in all these horrible stuff. But above it, I translate the application again from PA RISC to PA RISC, from one version of the processor to the same version of the processor, but collecting every information that I can. And is a very funny idea, right? Because I can do exactly the kind of things that we have described for VLIWs, finding traces, figuring out what can be done better. One of the things could be specialization, right? Monitoring the fact what values do I send to functions, and maybe I discover that I always call this function with essentially the same parameters, or one of the parameters is almost always the same, right? And so I can specialize the the function by sort of splitting in two, and depending on the value of that parameter of the argument that I use when I call it, I either go in the original function or I go in a recompile function where I do a constant propagation through the function, right? I assume that one of the argument is a specific value, and I propagate the constant and I simplify. That, just to make a silly example, right? Imagine that there is a function that does the square root, and I tend to call it always with 4 as an argument, but not always, right? But most 4. And now what I do it is that I change the original code of the square root function by making a test at the beginning. If they ask me for 4, if the argument is 4, the result is 2, and I don't do absolutely anything else. If the value is not 4, I do exactly the usual job, right? It's something that actually in some very specific cases is actually already done in libraries, but only in very specific cases that have nothing to do with the use I do. Maybe I call always the square root with the value 4 in this specific run of the program where I have a very strange data set that implies this. Since I'm doing the optimization and recompilation for this run, I get an advantage that I will never see if I were to do some form of global profiling. So it's a form of doing all the things that we have seen in VLIW compilation, in this kind of advanced compilers that we were studying in the last couple of weeks, but with two differences. One, we can actually be even more extreme, like, as I say, profiling and specializing functions. And the second is invisible from the users, because at this point, I'm not asking the user, please profile the code, send me all the information from gprof so that I recompile it well, and so on. It's completely transparent. And there is the ultimate advantage and point that is here at the bottom of the slide. If I'm not managing to do a good job, I can always bail out and forget about it, right? I can run the original code, and I cannot be worse than that. So here is an example of what Dynamo can do, and you have the speed up relative to the original code. And as you see, apart from additional whatever it is without optimization and so on, but you get a reasonable speed up. Is not completely dramatic, right? You're not going twice as fast, but remember, it is the same processor, right? You have already code that you have already compiled for this processor, but you do manage to go maybe 20% faster. And in the cases where you are slightly negative is because you figure out that you don't manage, and then you bail out, but you lost a little time, so you have a little speed down, right? There is a caveat that needs to be mentioned about this graph. This is, and is written in a couple of places, is over -0.2. So it's not the most advanced optimization of the compiler, is against a relatively, well, is a medium a medium optimization, right? It's not the GCC run in the easiest way, but it's not the best. So I think actually in the paper, these people explain that if you do it over the code in -0.4, that is the perfect compilation, actually you don't gain much or at all, right? But I think the philosophy, the idea is very nice. And here is an example of what happens with a couple of programs, right? What is the overhead that you have? And you see the example of MM80K sim of simulator, where you have only a very minimal overhead that is spent now and then to recompile. So very much at the beginning, because you decide to recompile immediately. Then every now and then, probably when around 100, you have a peak, because probably you go and touch for some reason a piece of code that you never touched. So you do another big translation, recompilation, optimization. And you see here the example of Go. I don't know exactly why, probably because it's a code that has a lot of control domination, and again visits a lot of different pieces of code in a very irregular way. You have this overhead that continues and never goes down to quasi zero. And that's one of the cases where after a while that you try to do it and you are not happy, you can say, okay, forget it. Let's run the program as it was. It's the best I can do. Now, I have been teaching this for many years because I think it is a cute idea, and I always thought that it was an idea worth thinking about, independently from whatever people do or will do these days. As I said before, I think the interest that I see in this is that it really helps you to challenge your own beliefs of where the software hardware border is or should be, or the threshold to switch from one to the other is, right? It changes. It's very much technology dependent, context dependent, and so we should always be ready to change it. But so I taught this for years, and actually in the meantime, or maybe already when I started teaching this course, Transmeta was already dead. My little revenge came when a few years ago, NVIDIA entered the ARM market by designing their own ARM processor, ARM V8, and decided to go for the same idea. You see in this slide a bit how the architecture works, right? You have essentially a simple in-order superscalar in the sense that it fetches 2 instructions per cycle and schedules. The scheduler is extremely trivial. It's simply the check data dependencies and installs one of the 2 or both instructions depending on the situation in the pipeline. So it's as trivial probably as the kind of circuitry that we were writing in the first, second course, weeks of this course a few months ago. So all this is extremely simple, except that there is a second path that things can take in the instruction can take in the decoding for a different type of instructions that are actually not ARM instructions, but some special encoding, a special mode invented and created by NVIDIA for this processor, where fetching the equivalent of 2 instructions, actually it fetches 7 micro operations, and these micro operations are practically almost not decoded. They are expanded in the sense that probably they are not this, so there must be some sort of clever encoding of combination of different instructions, but essentially apart from these expansions, the expansion is sent to the scheduler that has exactly the bandwidth of 7 microops toward the units, right? The units are actually, if you count them, they are exactly 7, which makes sense. So the point is that you can specify, probably with some constraints, what every unit does. So you can read this processor as 2 completely different paths and processor, the one made by these 2 decoders and the rest, which is a simple, not particularly good probably, but semi-decent in-order superscalar, and the processor that is done by this microcode expander and again everything else, which is a pure sort of simple VLIW, right? I have 7 units and I specify what these 7 units do, with or without, I don't know exactly the details, the ability of the scheduler to maybe withhold some of them if they have dependencies, or maybe not even this guarantee. So now I can go in both ways. It can be both. They are highly compatible because essentially they are the same operation and the same code, but encoded in different ways. And of course, I start in the mode where I use this, and then and this is the code that is made available to me from the user, right, the binary code of the source. And then on top of that, what NVIDIA has built is exactly the same dynamic binary translation engine, but essentially probably more similar to Dynamo than to the DAISY virtual machine. There is this in the sort of higher level of the uh, application execution, that when I see that I have opportunities, I probably collect some information about the execution inside the machine, and then I call a compiler, a recompiler that dynamically converts the code in bundles for VLIW, and then I can go and execute those bundles instead of the original program and get all the benefit from the machine. So it's essentially exactly the same idea, simply put in a context where, in a sense, probably is in between the Transmeta extreme case where I have really different machines and really I pretend I am a processor exactly like the x86, but I am not, and I have software inside. So that was one extreme, and the other extreme is this Dynamo that I was discussing before, where I'm actually not translating too much and actually not translating at all, but only optimizing. Here I am a bit in the middle, right? I'm actually really translating and really getting a performance advantage from the parallelism, but I'm still sitting in sort of the same processor. I have the possibility of executing native code, so I don't emulate anymore, right? Now I execute natively ARM code in an inefficient way, and then I switch to the translation only for performance reasons. And it works. This is, I think this is a commercial information, so it's not it's an infomercial, not scientific information, but it's still interesting and nice to see because it gives us a sense of what we expect to happen and can happen, right? So this is time that works, that runs, and this is by probably periods in the execution run, how much time is spent in the different tasks. I notice now that there are more colors than in the Legenda. I'm not sure where they got lost. I think you have the paper on Moodle, but what is interesting to see is that you start by spending a lot of time in the execution of the optimizer and executing inefficiently on the ARM, on this not particularly performant ARM, and very small time you manage to use the optimized microcode. But then as time passes, you execute less and less the optimizer, you execute less and less source code, and you're executing only mostly optimized code. And then every now and then you go, whatever is the benchmark, I don't think it is even said, but after a while something happened that brings you in a different part of the code, so you have to sort of restart from scratch, and then it goes to 0 and so on and so forth. But ideally after a while you are only executing optimized code, and therefore you're extremely efficient. Okay, this is the end of what I wanted to tell you. You have here maybe some other graph that you can check